Simple pendulum. A simple pendulum consists of a mass, and another name for that is the pendulum bob, at the end of a lightweight cord. Assume that the cord does not stretch and its mass is negligible, and so negligible that we'll call it zero. In order to be in simple harmonic motion, a system must have a restoring force that is proportional to the negative of the displacement. So what does that mean? It has to be proportional to something like this, minus kx. In this case, for the simple pendulum, and we go over this in more detail in the unit presentation, we have a couple forces acting on this pendulum bob over here. We have the tension of the string going up the string, and then we have mg. We do a little vector resolution, and this is covered really more in AP1 and also in APC, but for now, let's just say the restoring force is mg sine theta. You may not be covering that in algebra-based physics. So let's just put that there, and then say that the force that's restoring us is minus mg sine theta. And again, this is a little above algebra-based physics, but let's just present the material here to show our results. Notice that this is not a function of x. It's a function of sine theta. It is not a linear function. Okay, here's f equals kx, that's linear. Sine goes back and forth like that. So what do we do? If the pendulum bob is only displaced by an angle up to 15 degrees, this is a true relationship here. We call that the small angular approximation. The next thing we do is the definition of radians, again a little above the algebra-based physics course, but we know that x is equal to L theta. Right, there's L, there's theta, and x is how much you've displaced it, how much it's moving. So we're going to replace sine theta first with theta, right, over here, and then theta is x over L. So when we make the substitutions, we find out our force is pretty close to minus mg over L times x. So this should start looking a little bit like the simple harmonic motion for a spring, which is minus kx. So let's go to the next page. Here is another great example of where math is really, really cool. We've got this for the mass spring oscillator, and we know that's simple harmonic motion. We now have this with the simple pendulum, where we did a little bit more mathematics to get to that result. Look at those two things. We have x, we have x. We have force, we have force. We can then say mathematically that this mg over L behaves exactly as k does. So we have this expression for our spring mass period. So we go ahead and substitute in for k this value. Mathematically you can do that, and it turns out physically this works also. You go over here, do a little rearrangement, and we now have the period of a simple pendulum. Biggest factor here, the m cancels out. The mass of the pendulum bob does not affect the period. To reinforce that statement, as long as the cord is considered massless, and we're making that assumption, and the amplitude of the oscillation, that's the degrees that you move out from the vertical, as long as that is small, less than 15 degrees, the period does not depend on the mass of the pendulum bob.